CJ later, anything from the marking that you want to check with me, you just stay back a bit to check with me. Otherwise, let's do it. Okay, so let's look at question number 5. We skipped to drawing last week, so let's go back to number 5. Okay, when it comes to heat transfer, do remember, other than radiation, everything else require a medium. So the question here says vacuum reduces heat gain. Okay, so mainly because the two processes that require the medium, convection and conduction, will not be able to pass through the site because of a lack of medium. So I'll start by saying that no particles in vacuum. And because of that, right, convection, conduction cannot take place. So anything along the side cannot take place. Of course, convection, conduction can still take place over here, just that on the side. So we cannot totally say that conduction and convection is totally eliminated because there's still the top over here. So all we can say is that in this case, right, hence, because this is cold water, do not say heat loss. Cold water means that heat is coming in from the outside. That's why the question says heat gain and not heat loss. So we'll just mention that heat gain by, I will use the term conduction and convection is reduced. Okay, part B talks about the air above the cold water. That means they are talking about this part here. Okay, they are talking about this portion. The air that's directly above, okay, this thing actually is they are basically cold air. Because directly above the cold water, the air above is cold. So generally, because of that, right, the cold air above the water, they should be denser than the surrounding air. Okay, and because it's denser than the surrounding air, it create like a buffer. So hot air rises, all this thing doesn't work. So convection technically is unable to process from here. The hot air cannot enter because of this buffer, because the density of the cold air is higher than the surrounding. No convection current can be set up. Okay, so I'll say that since no convection currents can be set up, then I'll mention heat gain through convection is reduced. And I will also mention that air is a poor conductor. As we mentioned, it acts like a buffer, right? So air is a poor conductor of heat, and this also means that there will also be reduced heat gain by conduction. So this cold air buffer thing basically prevents convection currents from setting up, and as a poor conductor of heat, it is able to shield the heat away from the cold water. Something like that. In fact, right, this question in O levels, it also mentions something like this. Kaylee, do you know why? Okay, for questions like this, right, sometimes they have a stopper. Okay, this is nothing to do with the question already. So sometimes questions, they actually say that there's a stopper. Okay, so the stopper over here, you know the role of the stopper. And normally the stopper we also say is plastic. And for plastic, because it's a material thing, right, we say that same reason of poor conductor. Now what does the role of the stopper do? I mean, with a stopper, it actually helps to prevent heat exchanges. But a stopper technically prevent which process from happening. Any idea? Yeah, so that means like prevent like air movement, right? So the role of the stopper is the same thing. Whether is so the role of the stopper is also to reduce heat loss by convection. Oops. Okay, heat loss by convection. And this is especially true if the liquid, right, is actually hot. Because hot, then the air above will be hot, then all the hot air rises and things like that. So normally that's the role of the stopper. So TJ, based on cold water, right? This cold water setup, do you think it is necessary to have a stopper for this? If you want to keep the water cold in this setup, do you think it's necessary to have a stopper? This is an actual, I can't remember it's O level or school question. Actually, for this cold water setup, right? The stopper actually not necessary, because the layer of the cold air above is like the stopper already. Just now we mentioned this, remember? This cold layer of air here. This actually kind of function like a stopper already. This is actually like a stopper because it prevents, you see, the role of the stopper, poor conductor. Air, also poor conductor, like what we have written over here. Then it reduces heat by convection. Same thing if this is a cold water setup, the air above here is cold, so it also prevents convection current from setting up. So technically, right, when you are faced with this question, please remember, in this setup here, if your water is cold water, then the role of the stopper is not so significant. You can actually not use a stopper and it still kind of work because of this red layer of air above that is cold. However, if your water inside is hot, then all the convection current prevention and all those stuff, right, doesn't work already. Because your hot air will rise, then it will go off already. Okay, so in a nutshell, if your water is cold, then the effect of an actual stopper is less. But when your water inside is hot, then if you want to reduce all those convection stuff, the stopper is required. CJ understand? Haley understand? This one quite scary. It came out once or twice only. Yeah, can I leave this screen here? Let you all jot down whatever you all need. If you're ready, you can go to number 6. All right. Number 6. Okay, this is charging by friction. So if the rod is positive, that means the cloth must have turned negative. So in simple terms, electrons move over. So we'll talk about the electron transfer. I'll measure from the rod from the rod to the steel cloth. So now we'll mention that the rod itself has more positive and negative charges. So hence it becomes positively charged. Okay, this is your charging by friction, and it's only for insulators. Part 2 says that you try to charge an iron rod in the same way. So the iron rod being a conductor, okay, it's not able to retain the charges to keep them that way. So being an insulator, we can use charging by friction to forcefully transfer the electron between the two materials. So let's talk about, it's essentially just an earthing process. So if this is an insulator, okay, let's say this is the plastic rod. The positive charges can stay. But if this is a metal rod, if we try to charge it plus, the electrons will actually move from the ground up the person's body to neutralize this. So end results will be the rod will become neutral again. So and that this happens because as a conductor, it allows charges to move in and out. In the case of the conductor, the plastic, even if the electrons want to move, it cannot enter. Okay, electrons cannot enter because it's an insulator. So in this case, you'll mention that because the iron rod is a conductor and the you say the charges are earth, by his hand that's holding on to the rod. That's all. So do remember charging by friction only for insulators. And this is to explain why metal doesn't work. Okay, if number 6 is all right. Yeah, next page is I think induction. You take a look at 6B once you're ready. All right, let's look at B. So light conducting sphere X brought close to an insulating strand and X is strongly positive. Okay, so neutral sphere, draw the charges on 1. So you can have an induction, so it doesn't matter what's the charge on X, we just know that this is a very big plus. So it's going to cause the electrons to be attracted and this side becomes relatively positive due to the electrons running away. Okay, remember same number of plus and minus in the diagram. So X brought closer as observed that X will swing towards Y and touches after they touch they go away. Okay, this one do many times already. It's due to the unlike and then because of the unlike charges they attract and then when they touch electrons will move into the X. Then Y become positively charged and they repel off. Okay, so this one pretty straightforward. Okay, so I just give you the write-up. So first step, I'll talk about the induction. So we will say they form induced negative charges Okay, then we will say that due to unlike charges, they attract. So we'll say that X will move towards Y. Okay, when X touches Y, uh, we will mention that the electrons will move from Y to X. And now X, and because of this movement, Y will become positively charged. Okay, so because of this, the last part due to like charges, they will move apart. That's all. Okay, jot a quick one, then we go to number 8. Okay, take a look at question 8, the story. There's two different diameters and radius. Okay, let's look at number 8. So resistance technically is a ratio number only. Okay, it's the ratio between the potential difference across the resistor this OPD between the across the resistor and the current passing through it. Okay, so three factors that affect resistance: the standard length, uh, thickness, resistivity. These are three usual one. Actually, there's number four also, temperature. Okay, so or how to get R increase in all cases, length increase, thickness drop, high resistivity, and high temperature. Okay, the relationship between current and the marked section XY. So this thing here is a resistor because this one is in series. So in this case, the current the concept is that series, we have the same current. Nothing much. This is just two resistors. So this is a smaller R. This is a bigger one because of the larger circumference and everything. The length of the resistor is longer. Okay, for D, um, each of the two cross sections is at a higher temperature after a round. Okay, I'll say that the X will be hotter. Okay, simply because it has a smaller, uh, sorry, it has a larger resistance. Okay, so because of the resistance is higher, so if you talk about the power loss equals to I square R. So for the same current, but when resistance is higher, you have a larger power loss. Okay, and the reason mainly is because of the thickness, the radius of X and the radius of Y. All right, if no questions, please jot this down, then we go to number 9. CJ just to check, next part is something like a circuit breaker like that, or it can be a relay. The idea is the same. So my question is, you notice that it doesn't really, the solenoid doesn't really attract. And then we see that sometimes when currents is stronger, or for some reason there's a sudden surge of currents, then the magnetic field will be able to attract. So CJ, my question for you is, under normal circumstances, do we even have a magnetic field present? Hmm? Uh, yeah, so CJ, what's saying? So if this thing is working normally, that means there's no magnetic field, is it? That's why it doesn't attract, doesn't do any of those stuff. Then where did the magnetic field go to? I thought got current, got solenoid, sure got magnetic field. Okay, the one is okay when we talk about let me stray off a bit to circuit breaker. If you all remember circuit breaker, there's always like a contact point and then there's a solenoid here. So under normal current flow, the current can flow through and all right? Here under normal currents. So the contact doesn't break. Then what happens is that when the current is becoming like too high, then this contact will be attracted, that kind of stuff, then the contact is broken. So does it mean that under normal currents time, right, there's no magnetic field? Yeah, CJ, is this true? That's why the contact wasn't broken under normal currents. It's only when there's elevated currents, then there's magnetic field. What do you think about this statement? No means what? Well, no means got current or got magnetic field or don't have. Got magnetic field, but how come never attract it open? Only when the current is elevated, then you attract. Yay. Normal currents, magnetic field is not strong enough. Correct. Then currents increase, the strength of magnetic field increases, then it becomes like strong enough. Okay, so just a quick straight off. Do remember this. Okay, so how the switch allow it the door to be open? So you can see that when you press the switch, the circuit is closed, current flows through the solenoid. Okay, so we need to mention, okay, when it's pressed, the switch is closed, current will flow in the solenoid, and because of this, there'll be a magnetic field around the solenoid. Then we'll say that the iron core okay, so when it becomes an electromagnet, then we will say that it will attract the using the iron bolt. Okay, and because of this, allowing. Okay, so the iron bolt is changed and then a thicker piece of iron is used. When the switch is closed, it remains locked. Remains locked simply means not strong enough to pull it off. So how to make it strong enough? There are three ways you can make it stronger. The usual answer, increase the size of the current. Okay, this can be easily increase the number of batteries. Number two, increase the number of turns. Okay, and number three, you can electromagnetic iron, they call it iron bolt. Bring it closer makes it easier. So the same theory also goes for the circuit breaker. I think this one we have done a few times already, but just do it one more time here. So let's say the trigger current is 15A. When it's 15A, you're strong enough to pull it. So if I want to change the trigger to 17A, okay, so I want it to trigger at a higher current. So I must make it harder for it to trigger. Okay, make it harder to trigger so that the trigger current needs to go even higher before this circuit breaker can work. So things that we can do to let it trigger at higher temperature will be number one, reduce the number of turns. Okay, we can also bring the electromagnet further away from the contact point. So this again needs a higher current to trigger. Now, if you want it to trigger at a lower current, that means easier to trigger, then you assist it by increasing the number of turns and you assist it by bringing the EM nearer. All right, then part two, explain the changes. Okay, generally all the changes that we do, right? Okay, all the changes actually increases of the magnetic field, or we can say that uh, bringing the electromagnet closer Okay, so when you bring the electromagnet closer, then it will be easier for the magnetic field to interact with the bolt. Okay, easier interaction, and the other one will be the increased strength of magnetic field. Okay, if 没有 question, can I give you a few minutes to try out question 10? This one is quite a question 10 is quite a good question. Okay, can I give you about 12 minutes to finish it, then we go through together. So if you look at all the forces, right, the question wants the tension. So there's a upward force tension, there's a downward force, which is the weight. And then overall it's accelerating upwards. That means there's a resultant force upwards. So over here, I can put resultant force equals to tension minus the weight. So resultant force, the question says is accelerating up 0.61 for 2.6 seconds. And then the total mass of the entire thing is 610 kg. So that gives me the resultant force. So if you just use F equals to ma, it's not good enough. That's not the tension. So resultant force here is 680, which is the mass multiplied by the acceleration. Okay, tension minus away the weight. The weight is 680 times 10. Then you bring over, you'll be 7210 newtons. CJ, you do it this way? Kaylee, understand? Do remember, F net is not equals to tension. Kaylee, you got it? CJ, you use the same concept. Okay, good. Okay, can. Okay, I'll give you all the values for the next part. Okay, let's do C first. It says, does the acceleration affect the profile of the comfort? So sometimes you talk about the lift, right? Those lifts that move very fast, it makes us very uncomfortable. It's the same effect. So you say that if the acceleration is too large, okay, we'll say that the net force acting on the passengers, it will be too large for comfort. That's all. Okay, numerical values for D, E, F. I think D, F, yeah. Okay, all these are again 3SF. Okay, F is not well done. Okay, these are the three values. You'll try and see. So for this energy from level 1 to level 5, so energy basically power times time. Power is 7,100. Given over here. And the time of ascent, it says it takes 14 seconds. So just throw in the numbers only. So 99,400 joules. Okay, calculate the constant speed. So this one we use V minus U over T. It starts from rest, it accelerated only for 2.6, then after that, no more acceleration. So also pretty straightforward, 0.61. The V answer over this time taken, the acceleration took 2.6 seconds. So we have 1.59 meters per second. Okay, and for part F, the height gain is 30 meters. Calculate the useful power. So the useful power, because initially on top, right, we have the power equals to this. But useful power is different. It's the actual energy used to raise it up. So energy that's required to raise it up, right, will be, because this is a gravitational potential, this is mgh. So the total mass 680 times 10 times 13. Okay, this is our total energy. So the actual power that is useful is the useful energy, which is to do the work. So it's actually this energy, same energy here, divided by 14. So from here, I get 6310 watts. And of course, it will be different. How come you need to put in more than you need? So this is always energy needed, okay, to overcome. Okay, because this is a lift question, I will go for overcome the friction between the moving mechanical parts of the lift. 1.54 meters per second, 1.59 meter per second, quite slow. So I think the effect of air resistance not that much. I mean, when you take the lift, you don't feel so much speed such that you can feel the wind blowing, pushing against your face. So most likely it's all the mechanical, and lift also produce sound, right? So there could also be the sound produced, energy loss due to the sound produced by the moving parts. Okay, so all these account for the difference in the power. So the actual power required is 6310 if there is no friction. So with friction, there's actually energy loss, 7,100 is needed for the lift to move up a height of 13 meters. Yeah, that's all. Haley, okay? Okay, this one, EMF, right? We are using the E equals to VQ to explain. So V equals to E over Q. This is work done. This is charge. Because it's EMF, we say that this is actually the work done to move or to drive unit charge around the entire circuit. Now, if it says what is potential difference, then it's also the same work done to drive unit charge. Then in this case, you'll be through the component. Because normally potential difference is for two components. Okay, so the advantage. Or rather using a single 2 volt. Okay, whether this is in this way, right? Or it is just like this 2 volts. Okay, in both cases, this EMF is 2 volts. This EMF is also 2 volts. Okay, so state one advantage. There are three advantages. Okay, can you all just let me know what you all think are the advantages? There are three of them. See whether you can think of all three. There's one that every year everyone can say, and so the other two, see whether you all know how to do it. Yeah, whatever you all think is the advantage. Yeah, please let me know. But do know, regardless of whether is it two batteries in parallel or just a single 2 volt, the EMF will be 2 volts. It's the same. So electrically, nothing change. So what's the advantage of doing two in parallel? Yeah, whatever answers you have, yeah, please let me know. Then I'll add on to the three advantages. So the two batteries that are in parallel together, remember anytime we add a branch, the effective resistance is lower. So number two, it actually reduces the internal resistance of the cells. So this will actually enable um, lesser energy loss due to the resistance of the batteries. Okay, I give you the third one. Basically, when the two batteries are in parallel, right, there's generally a larger combined power, which means that without without any sort of replacement, they can actually last longer. Okay, that's all. Okay, next part, the calculation. Can I get you all to try it out first? CT, okay, the three reasons. We look at it very straightforward from there. Okay, DC is 12. Current is, okay, this one is 12 volts. This one is 1.5. Then the student changed the EMF to 6. And then the lamp become dimmer. Should be become dimmer because power equals to IV. So naturally, okay, based on this, I just do a very rough calculation. If you do V equals to IR, 12 divided by 1.5, this guy is 8 ohms, okay? So from here, the brightness at this point is 12 times 1.5, 18 watts. So you have 18 watts worth of electrical power. Okay? Now I'm going to do something that's wrong, but it feels like this. This is the general wrong answer that is produced. So very, very logical. If I have a new EMF of 6, then logically this one should drop to 7.5. And then when I do my power, 6 times 3/4, okay, 2, 3, 4.5 watts. So you notice that in this case it becomes dim. Seems like correct, dim, and the ammeter fall below 1.5. So fall below 1.5 means 0.75 is less. This is the general scenario that most logically you would think like this. Okay, CJ, this angle makes sense or not? Based on this scenario, I will choose 0.75 ampere. Make sense? This one need to make sense first, then the logic will come in. And Kaylee, this is the angle that you take, right? That's why you say that it will be equal to 0.75. Because 6/8 is 0.75. Okay, CC does 0.75 make sense? Okay, but this is totally wrong. Okay, I need you all to just take a look at whatever is over here. Not just my number, also look at the question. Can you all find what is that one thing that may make whatever that we did here totally wrong? And that's because you all assume one thing. This one is a conceptual thing, right? Can you all find what is the thing over within the blue box that could be the sheet stirrer? Can you all find the sheet stirrer? Once you found the sheet stirrer, the answer is actually more than 0.75. Okay, the answer is more than 0.758. Going by this logic, change to 6 volts. What could have happened that caused your currents to be more than 0.75 when whatever that we calculate here totally prove that it's 0.75? Under what kind of situation will you get a numerical value more than 0.75? After we adjust the EMF to 6 volt, what could have made it to be more than 0.75? Go by the mathematical logic, how do I get more than 0.75? And then look for the sheet stirrer and see whether you all can link the whole big picture together. They say you found the sheet stirrer. The sheet stirrer is they say if I give you a hint, don't follow Ohm's law. What comes to your mind? Does filament comes to your mind when you see doesn't follow Ohm's law? Not the lamp, the filament, specifically filament. Okay, let me do a run through for this. Let me draw the V against I graph for for this particular non-ohmic lamp. Okay, filament. Okay, I'll just do a quick background. Okay, anyway, last question for today. So you'll just concentrate a bit more. Filament lamp is this one, okay? And then you have this wire nonsense, and then you have the light bulb. So this thing here is a filament. It's made of tungsten, and this guy doesn't follow Ohm's law. Doesn't follow Ohm's law means that the resistance is not constant. So when you look at the VI graph for a filament lamp, right? Okay, remember if it's a VI graph, the gradient equals to resistance. So initially, it follow Ohm's law. Okay, then when the current increases to a certain point, it start to spike up already. So what this graph tells you is that when current increase, right, resistance will start to rise. And similarly, if current fall, resistance will start to fall. This is for the concept of a filament. Okay. You also have to be mindful if the graph is a IV graph. Okay, because I over V is equals to gradient. Therefore, V over I is 1 over gradient, which is resistance. So for this curve, right, you have something like this, then it becomes more gentle. More gentle also means, this also means resistance rise, because it's 1 over the gradient. Okay, don't forget that 1 over the gradient is actually the resistance. Whereas for the other case, this one is also resistance rise. Okay, we just switch the axis only. So you'll be mindful of this. Don't be trapped by the shape of the graph. You need to look at the axis. Okay, you could be given IV or VI. Okay, interpreting the axis in the wrong way will destroy your answers. Okay, so I'll give you my answer for this first. Why is it more than 0.75? Then I'll just show you a quick number. Okay, so in this case, I'll just mention that because the EMF is reduced, the current through the filament will also decrease. Okay, this one is standard. And because this one decreases, right, the temperature of the filament due to the lower currents will also decrease. And this will lead to the decrease in the resistance of the filament. Okay, then using current equals to V over R. And then we say since V is halved, but R also decreases, therefore the new currents will be greater than 0.75 A. Okay, as a side note, if it is ohmic, then the current will be 0.75 A, since resistance never change. But because this guy is non-ohmic, it changes. That's why the currents will be a bit higher. Okay, I'll give you all the mathematical proof for this. Later I'll scroll up. So let's say this one is 6 volt. Okay, as mentioned, right? Supposed to be in purple. Purple is the original. Then blue is supposed to be the one where it changes. So what actually happens is in black. So resistance was 8, right? But because of the lower current, lower everything, right? Maybe the resistance dropped to 6 ohms. So the actual current is not 0.75. Okay, it's going to be 1 ampere. So when you calculate power equals to VI, 6 times 1, I get 6 watts. Yes, it's still going to be dimmer because original is 18 watts. So it's going to be dimmer even though the current flowing through is not half, it's actually 1. So this is due to the fact that, as what we mentioned, the lower currents means that the temperature of the tungsten filament is actually lower, which leads to a decrease in the temperature. And this leads to a decrease in the resistance of the filament. So this thing becomes adjustable. And that's why our values will not be exactly half, because our resistance do change. Okay, so um, this is the check that you need you all to understand. Okay, so the IV curve I'll spread up later, but help me jot this down. This is the explanation and the write up. Kaylee, understand? Did you understand? Concept is non-ohmic lamp. No, filament are made of tungsten. Tungsten, although it's a metal, right? But as a filament, it is non-ohmic. If it's just a normal piece of straight out fixed resistor, fixed resistor will be considered ohmic. But tungsten filament is non-ohmic. And the reason why tungsten filament is non-ohmic, right, is because tungsten naturally has a high it's a high resistance material. So it creates so much heat, right, that the resistance changes. Because one of the things that will change the resistance of a metal is temperature. The higher the temperature, the higher the resistance. Most of the time, most metals are fine. But for certain material like tungsten, which is used in a filament of a lamp, the effect is very, very pronounced. Yeah. But across the board, all metals, right? When temperature rise, the resistance will rise. Haley, you know why? If the question asks you to explain why is it that when the temperature rise, the currents, temperature rise, resistance rise, which leads to lower currents. For generic metals, do you know how to explain? CT also, you know how to explain why temperature rise, resistance of metals will rise. Oh, CJ, listen again. Generally, resistance of metal increases when temperature rise. But why? The answer is a very molecular answer. You all got to zone into the what do you mean by indices of metal? Resistance or resistance. Resistance, not indices. When my nose has been blocked for 3, 4 days, and yesterday I lost my voice. Yeah, maybe a bit muffled. Okay. Again, temperature rise, resistance of metals rise. How come? Kaylee almost there already. Almost there. Mm. CT, you can come up with a reason? Then I'll just explain uh the metal thing. Basically, resistance is like how easy the electrons can run around. So generally, temperature rise, the electrons find very hard to run around. Yeah, you probably heard it before. You think of it as a path, or like a walk path for you. Okay, your want your objective very simple. Okay, you want to walk all the way until this point. Okay, your objective is to walk across this path. Now, in this path, there are a lot of people also. So there's people 1, people 2, people 3, 4. They are also walking with you. Okay. Then, for you to navigate through all these people, right? CJ, do you think it's easier for you to navigate across these people if they are slow or if they are fast? They are moving around quickly or moving around slowly. Which one is easier for you to navigate through the path? Slow, slow, then you can move around them, the particles. Correct? So, Kaylee, you focus on the kinetic energy of the electrons, but it's also because of the metal atoms. These are like the metal atoms. Because temperature rise, the atoms itself, they vibrate faster. So when they vibrate faster, they're like all over the place. Okay, they are fixed position, but still they are like vibrating very, very fast. So for the electron, right, that try to move across, when the particles are like moving, vibrating so fast, right, instead of a generally straight path for the electron to go through, maybe the electron need to navigate around the very fast vibrating particles. So it becomes very, very difficult for the electrons to flow through. So when the temperature is high, they vibrate faster. So it makes it harder for the electrons to flow. This means that resistance has increased because the particular vibration, okay, the particle vibration of the metal actually becomes faster. And for them to navigate around the more energetic particles is actually harder. That's why we say that metals generally resistance increases when temperature rise. It's just that for all metals it works like that. Wire also like that. That's why wire get heated up, the resistance also rise. That's also the same for normal fixed resistor. But for tungsten filament, it's very pronounced. Their temperature rise is very, very, very uh significant. That's why it falls under the category of non-ohmic conductor, which is used as a teaching point for our syllabus. Okay, but generally, you all can put a point here to say that it's due to the more active or more vigorous uh, atomic vibration of the atoms and makes it harder for the electrons to flow. And hence, this shows that the uh, the resistance is higher. Okay, and to blow your mind further, I don't know whether you're linked to this or not. Q equals to IT. Okay, so I equals to Q over T. Q is charge, charge is carried by electrons. So if they have difficulty flowing through, right, that means that there's less electron flowing through for the same amount of time at high temperature. And because of this, the amount of charges that can flow through, because the electron find very hard to flow through, so less electron will flow through for the same amount of time. So the charge will drop for the same amount of time, the currents drop. So this also shows that when the current is, or rather when the temperature is higher, the resistance goes higher. That's why the current drops too. So it all tangled together. So that's how you can see also. And quantitatively, using Q equals to IT, the drop in the charge for the same amount of time will give you a lower current also, which indicates a higher resistance. Something like this. Okay, if nothing else, I think this is our last question for tonight, today. You all jot down whatever you all need, and then that's all. Any questions, please ask before you run off. Otherwise, thanks for coming, girls.